I'd like to introduce the first speaker for the second half of this morning's session, Peter Schlosser, who's a professor at Columbia University. He's the Director of Research of Columbia's Earth Institute and is also a senior research faculty with the Lamont Doherty Earth Observatory. His research has been focused on the various aspects of water, both ocean water, groundwater, water in the atmosphere, and use of various types of tracer techniques to study changes in the water cycle in the context of both anthropogenic and natural change. And he's also looked recently at engineering approaches to mitigating and adapting to some of these changes. As he already pointed out himself, he's been chairing the organizing committee for this meeting, and he's also the outgoing chair of the Search Science Steering Committee. So thank you, Peter.
Thank you, Hayo. Yeah, what I would like to do is to basically do two things in one talk. One is to talk a little bit about the kind of science that we need to address the questions that are coming from the what I call the solution domain, but also as I go through that, give you a little bit of feeling for how the conference has been set up and how these four themes are rolling into each other. So as I said, basically we'll go a little bit through the just a very brief introduction, then Arctic system studies, the changes linked to lower latitudes, the translation of our science into solutions, which are the four themes, and then sort of ponder a bit what kind of new approaches we actually might need to support or provide the scientific support for all the questions that are out there. If we're looking at the Arctic, of course there are some specific characters or characteristics of it. It is it has a landlocked ocean that's ice covered, has large ice masses on land, including Greenland, permafrost, it has vulnerable ecosystems and a long and rich culture, all things that we have already heard this morning. In the past, when thinking about the Arctic, a lot of people thought of it as a remote area that had exotic life forms, was challenging, pristine. But recently we really think about the Arctic not just among scientists, but more in the general public as an area that is undergoing rapid change, and we are wondering what all that means and what we can do about it and what it means for the global environment. Now all that should not have come as a surprise, because the early coupled model simulations of the global climate system, which actually were done in the early mid-80s, already showed something that also comes out in the latest IPCC assessment, and that is that we are seeing the consequences of anthropogenic activity, mainly the burning of fossil fuels, on a global scale, but we see it amplified in polar regions, specifically in the Arctic. So that is something that has been around since a long time, but for quite a while we really didn't pay too much attention to it. And that in spite of all that, we also have the situation that the Arctic has been data poor, still probably is compared to many other regions on the globe. And I'm just highlighting that using a publication by Jim Swift and others in JGR in 1987, where the picture of the hydrography of the Arctic Ocean, here from the surface to the depth for salinity and for the age structure, was still based on just a few locations where deep measurements were available from, typically the ice stations. That then changed in the 1980s, when expeditions of Polarstern, the Swedish icebreaker Oden, and the Louis Saint Laurent managed to cross the Arctic Ocean, and we basically got quite a bit of detail about the connectivity of the Arctic Ocean to the Atlantic here, with this warm water layer pushing in. We saw that there is a cold halocline, and there is quite a bit of stratification within that cold water layer due to river runoff and a precipitation over evaporation excess. But in spite of these emerging details, we are still in many parts of the Arctic, ocean, terrestrial system, human domain, we are short in knowledge about the very fundamental mechanisms that make this system function. And so there is a clear need for continued study of the basic system properties, and indeed there is still quite a bit of need for exploration, and I just highlighted that in two pictures. One is from the BSERP program, where basically the physical system is coupled to the biological system, which then feeds up into the human domain. And the exploration aspect, here we see a black smoker that was detected on the Guggle Ridge. And of course, due to limited access, these kind of features are still probably emerging over the next years and decades. And theme one of the conference will actually explore how far have we come with the understanding of the Arctic system and its subsystems, and where this science is heading. As we were starting to get a better feeling for the Arctic, and we actually at that time, I remember the mid-80s, we went up there sort of with this naive notion that we will study a system that is in a quasi-steady state. But of course the first expeditions actually showed that this system was actually moving, and not just in one domain but in all domains. And during the mid-late 80s and the 1990s, it was recognized that the Arctic is undergoing changes in the physical, biological and human domains across its system scale. And examples are increased air temperature, reduced sea ice cover, basically the known kind of features, ocean circulation changes, permafrost and Greenland Ice Sheet. Now these are pretty much characteristics of the physical side of the system, but it also has been recognized that there are large impacts on the ecosystems and society, and over the years we have accepted that we have to look at the anthropogenically driven change component and figure out how it evolves and how it interacts with the intrinsic natural variability that happens on all time scales. So just to remind you of some of these changes, this is the 2009 versus 1950 temperature anomaly. So we have about 2 or so degrees warming over that period, and that sort of, if we are looking at the global one, where we have about 0.6, 0.7 degrees, so it's about the 2 to 3 times amplification that we would expect. In terms of the ocean, we really had a big wake-up call in the 1990s when for the first time we could do system scale observations, which were enabled by the nuclear submarines, the SciSex expeditions. And these results from Jamie Morrison and co-workers show that we had salinification and a big temperature increase in the Atlantic water, moving pretty much throughout the Arctic Ocean, and also causing regime shifts between the Atlantic and Pacific domains. Sea ice, of course, is an iconic feature, and also the changes that have happened are well known. There was, during the past few years, quite a bit of attention focused on that. While we have a decadal decrease of about 11% or so per decade since quite a while, in 2007 we pretty much saw this drastic decrease by about 20%. And the question was, why was that? And in essence, it is the fact that this is a nonlinear system that can undergo abrupt changes. And if we would have read our long-term observations a little bit more cleverly, we actually should not have been that surprised, because there was a sort of a persistent flushing of multi-year sea ice, which is the green color here, out of the Arctic. This is the 81 to 2000 average, and then if we look at 2007, it was diminished, and it actually even in 2009, it covers a smaller area. So although we recovered in the extent to almost the 2005 level, the system is more vulnerable, and if we get another trigger event, we might drop quite significantly. Greenland Ice Sheet as another iconic feature of the Arctic. Well known that there is an increased area of the surface that is melting, but more importantly, we also know that now, from research during the past few years, that this surface melt is actually finding its way through crevices in certain areas all the way to the bedrock, and it basically makes the ice sheet around the fringes of of Greenland more slippery. So melt area is increasing, and the slip of the ice sheet is increasing, which basically then lets us wonder how much of that potential 7 meter of sea level rise might slip into the ocean on which timescales. And questions like that will be discussed in theme 2 of the conference, and we will hear about the newest findings and what we might have to conclude from them. There is of course also a connection to the global circulation. We already heard this from Mike Steele in Arden Bement's talk, this connection of the Arctic freshwater to the global conveyor belt. There was a great summary of the ASOF group that sort of summarized what the natural freshwater flux from high latitudes to the convection areas in the North Atlantic is. Roughly 283 millisverdrups, that's 10 to the 3 cubic meters per second. And if we are then looking at what we might expect in terms of additional freshwater sources, I made a little compilation here. Sea ice, river runoff, and P-E are actually not that large. The biggest source of fresh water that we have sitting up there is the Greenland Ice Sheet, so we have to watch the evolution of that ice sheet carefully, because if we would get a sustained addition in the area of 90 to 180 millisverdrups, we would be able to add enough fresh water to the lower latitudes that, according to model simulations, could decrease or potentially shut off the conveyor belt. Now, what that would do in the world without greenhouse gases, it would cool the atmosphere over the northern hemisphere. But because we have counteracting that effect the greenhouse gases, we probably just will see an offset of the warming, so a smaller warming because of this effect. And these topics will be discussed in theme 3 of the conference. Of course, we are seeing quite a bit of impacts from these changes. They are in the Arctic and in low latitudes. For example, sea level rise. Here we are in Miami. That's a projection of the ACIA. What by the end of the century will be submerged in water. But we do have changes in fisheries, land cover, erosion, infrastructure, vegetation zones, forest fires, etc. And these impacts, of course, lead to more urgency in solving some of the questions that are underlying the observed changes. Some of these we already have seen: eroding coastlines, fishery changes. Here we have cod possibly increasing, and then shrimp fisheries harvest probably going down according to our ability to project. So theme 4 will actually take on some of these questions of how well do we understand the impacts and how can we work on providing answers for that. Now, the question is, are we communicating the message? And it seems, looking at the press, from scientific magazines to more widely read publications, that the message is getting out there. The question is it penetrating? Is it heard? And how do we, as a society, react to it? And there is one article that came out just when the ACIA report in 2004 was released, and basically, I don't expect you to read any of that, I just wanted to highlight 2 passages. It concluded that ACIA painted a grim picture for the future of the Arctic, meaning that a lot of impacts will be seen. And then it speculated, saying, you know, the solution to this problem rests on our ability to imagine and purposefully shape the future. Now that is what earth engineering or geoengineering would be, and the question that is upon us and we have to discuss in theme 4 is to which extent do we actually have the scientific underpinning for such contemplations, and what can we actually do in principle and what should we contemplate. Now let me just move towards the last part of my talk and talk a little bit about new ways to approach this complex set of questions. And one of them, of course, is increased sophistication in synthesis of our results. In 2003, a group of scientists met, and looking at all the evidence that was available at that time, we concluded that the Arctic system is on a trajectory to a new seasonally ice-free state. I think that has been confirmed. It also showed that we really need more effort in the area of complex system theory and modeling to understand all these feedback loops. We need new technologies reaching from probes that can be deployed, autonomous vehicles, moored instruments, satellites, and possibly new icebreakers. We are in the middle of building a pan-Arctic observing system, and that is a challenge because it needs different kinds of funding streams. It has to include local and traditional knowledge, and it has to be done in international partnerships, because it's just such a huge effort that a single nation or a group of nations cannot master that. And it has to also capture the legacy of the IPY into the future. Not only is there the need for a pan-Arctic observing system in one domain, but it has to be integrated over ocean, atmosphere, ocean, sea ice, atmosphere, hydrology, and so on, and the human domain and paleo. And that is a challenge that we just have no template for. We have to figure out how to design these systems within each compartment and then across the compartment that we are used to. We do have a need for projections, because anything that we are doing with respect to sustainability or sustainable development requires that we have some knowledge about what the future state of the Arctic system might look like under specific development scenarios. So although we know first order projections pretty reasonably well within the error envelopes, we have the need to get projections on regional scales, on local scales, because that's where the effects are felt, and there is quite a bit of work to be done to increase our efforts in that area and to inform the modeling efforts that will produce these projections by the data streams that are coming off our observing systems. And that will link all 3 components together, the observing, understanding, and responding to change components that we were talking about. We have to include stakeholders in everything we are doing much more early, basically from the beginning. I just used this slide from Martin Jeffries about the Arctic Observing Network. There is a need for information on the scientific side, but also on the side of people who are living in the Arctic. And the focus right now is on the research observing. There is some community-based observing that's going into it, but we clearly have to increase our efforts to make this a more joint effort. So to sum up, I think it became clear during the morning session and before the conference even that Arctic change is real. understanding and responding to the change requires new approaches, and they include, and this is not a comprehensive list, but just some examples, new long-term observing systems and new technology for these observing systems. We need enhanced synthesis efforts, and we have to figure out how to actually define and drive forward what synthesis is. We need improved projections, and that for multiple scales, downscaling among them. We definitely need increased transdisciplinary approaches to research. International collaborations have to become the norm rather than something that we strive for here and there. We have to include local communities in everything we are doing. There is training and education that has to provide the next generation of scientists to deal with these questions. We need new partnerships between scientists and stakeholders, and we need new partnerships between scientists and funding agencies, because the type of work we are doing is different. Now, all these approaches will not substitute what we are doing in basic research right now, but will augment these efforts. So I will close with these comments.